All right, welcome back everyone. So this is the last day of part 3 of the 2-part statistical network analysis course, also the last day. Originally, I had wanted to focus today's lecture on some recent papers on spectral methods and extensions of what we discussed, but I feel like last lecture we were maybe a little bit rushed, and I thought it was maybe a better use of our time to slow down just a little bit, see some of the ideas, concepts and technical material in a little bit more detail. Right, so hopefully this will feel like a culmination of the entire course, but in particular these last 3 lectures focused on spectral methods. So last lecture, we talked about key ingredients for what is called often L2 perturbation theory. So perturbation theory in the L2 vector norm, or in the Frobenius norm for matrices, or an operator norm for matrices. Right? We encountered Weil's inequality for eigenvalues. We also encountered the Davis-Gahan theorem for subspaces, principal subspaces. We then briefly talked about and defined the so-called 2 to infinity norm. That's a norm that takes the L2 norms of the rows of a matrix and reports back the maximum. We briefly alluded to how that can be used to establish more fine-grained results. We're going to revisit all those concepts, but in a little bit more detail here. So hopefully the ideas, as well as the proof ideas, become a little bit clearer. So I really want to deliberately slow down today a little bit. Please, if you have questions, feel free to ask. Okay. So we started last lecture with this setup where we encountered a stylized adjacency matrix, or really an expected adjacency matrix that had very nice block structure, allowing us to visually isolate that it is rank 2, identify its 2 leading eigenvalues, eigenvectors. In the results that we proceeded to talk about and that we'll revisit here today, I mentioned this in words, but I wanted to put it on the board here. We're going to slightly transform this model purely for convenience, so that instead of being a rank 2 model at the expectation level, it's going to be just rank 1, meaning that the leading eigenvalue and eigenvector are now going to correspond precisely to this distinction between nodes in community 1 and nodes in community 2 on the basis of a sign change. Okay, plus and minus 1, and the corresponding eigenvalue indicates the separation or the discrepancy between the underlying distributions. Right? For SBM, here we're thinking about P and Q as the success probabilities, right? Those Bernoulli probabilities. Okay, so we mentioned a theorem last time. I think it's useful to spend just a few moments sketching out the proof because it builds directly on what we encountered in the previous notes. This theorem is for a very simple algorithm which simply computes the leading eigenvector from our data, right? And then applies a rounding scheme to the elements and just assigns the entries of the eigenvector. Well, we have this new vector called x, and the entries of x are simply 1 or -1 depending on whether the corresponding entry in our eigenvector is strictly positive or negative. Right? In this model, there are 2 communities, or 2 classes, if you will, and so this is what we're distinguishing here. Right? So we have a theorem which says that provided your graph is not too sparse and there's sufficient separation between the 2 distributions, then we can bound with high probability the fraction of misclustered nodes returned to us from this algorithm here. Right? So this is a high probability statement, meaning with probability tending to 1 as our matrix or graph grows in size. This is an overall fraction, right, of misclustered nodes. That fraction is going to 0. Maybe there is still, some logarithmic order of nodes that are getting misclustered, but at least the fraction is going to 0. Okay? So let's spend just a moment and sketch.
So Joshua, just one quick question.
Please.
Which is not exactly about what
Please.
But I mean, with this 2 to infinity theory, right?
Yep.
So we're
Yes, that's right. And we're going to see sort of the stylized version of that result a little bit later, so we can compare it with this. Perfect. Great. All right. And so these two observations, or these two hypotheses, really are going to be used together with the Davis-Gahan theorem and Wiles inequality. So let me just emphasize here with some colored chalk. This is our sort of key hypothesis in this setup. Okay? So by Wiles inequality and H, meaning this hypothesis, we have, with high probability, and again, high probability, for the sake of our discussion here, really looks like the form 1 minus big O n to the minus c, where c is some fixed constant that you can choose, 8, 10. I mean, usually we choose it larger than 2 so that you can apply Borel-Cantelli or some other type result, but we're not too concerned about sort of exactly that statement here. So by Wiles inequality for eigenvalues and H, we have that with high probability, the operator norm of our noise matrix. Remember that noise is just the difference of our observation and the expectation. This is less than or equal to hiding certain absolute constants. I'm going to use less sim equal to lambda star. Okay, where lambda star, remember, is n over 2 p minus q. So let's just recall that as less sim. Okay. So now, applying Davis-Gahan gives that with high probability, the distance between our sample eigenvector and the population eigenvector can be bounded. And the bound looks like an inverse signal-to-noise ratio, where the signal term is the eigenvalue magnitude and the noise term is the operator norm of E here. So we have this, just hiding a constant factor of 2 in this example, but less sim E an operator norm lambda star. But now plugging in the fact that we have an operator norm bound for this, remember from our previous discussion of operator norm bounds, this looks like order n here and p. We're assuming, for simplicity, p is greater than q. Here, in the denominator, we have n times p minus q. And in our setting, this is a little o1 quantity, right, as a result of the situation we have here. All right. Here, just to be a little bit more explicit, we're talking about a distance between u and u star. This is the L2 difference of these vectors where we have specified a choice of sign. Right, so here, our loss function was a statement with respect to alpha being should be an alpha xi star here. Alpha being a choice of sign flip. Here, we're just assuming for simplicity that we control the angle that u and u star make. That's just for convenience. Otherwise, we would say this is the minimum of this and the same quantity with a plus u star, right? But this is where the L2 terminology comes into play with respect to our distances. So now let's define a set N as just the collection of indices, all right, either indices in our eigenvector or corresponding nodes in the graph, so that the difference between the ith component of the sample eigenvector and the population eigenvector exceeds this threshold 1 over root n. Okay, so now let's go back to our algorithm and just remind ourselves of this rounding procedure that we have here. So in particular, we have a disagreement on node I when there is a difference of sign in the component of the sample eigenvector and the population eigenvector. If there's a difference of sign, that means let's look at the absolute difference between this component, and if there's a difference of sign, well, this is at least the magnitude of ui star, and we know that this is just 1 over root n. Why? Because all the elements of our population level eigenvector have magnitude 1 over root n. Okay? So what this does is this allows us to think about the cardinality of n, right? Again, n are the sort of the bad points or the sets or the indices where we exceed this threshold 1 over root n. So this is now a quantity that we can bound by the L2 norm squared divided by 1 over root n squared. Right, so just identifying what does it mean to be in this set, what are the possible values that this can take, and what is this bounded by, gives us this expression here. And this is a quantity that is little o n. Okay, so let's see. Just to give us enough room, we have this ratio or this fraction of misclustered nodes is bounded above by an expression that looks at differences between eigenvector components This gives us the cardinality of n, of capital N divided by n, and we just claim that this is a little O(n) term, so when we divide by n, this gives us little O(1). Right, so we're applying this hypothesis which says effectively that the graph is not too sparse. There's enough separation between the distributions. Then we apply Weil, Davis-Gahan, and we think about what does it mean to miscluster, right? And misclustering boils down here to an incorrect choice of sign, right? And this choice of sign is directly related to the sign of the entries of the eigenvector. And so we want to control then the number of these misclustered points by an expression that looks like the L2 norm of a difference of eigenvectors. And we claim that putting all these pieces together in this way establishes the result. Again, all of this holding on sort of good events, right? These high probability sets. Okay, so this is admittedly a bit of a sort of a rapid sketch, but the full details of this proof and theorem are in the reference Chen et al. 2021. That's where I've taken this example from. Okay. All right. So let's now go back to this quantity, the 2 to infinity norm. Okay. So for a matrix, let's say T, the 2 to infinity norm is defined in this way. Here I'm using T because it's conceptually useful to it's useful in practice to apply the 2 to infinity norm in situations where your matrix is tall and skinny. Okay. So this is now just a max. This is the max, I'll put it in words, of the L2 row norms of T. Okay, and some properties. If we're given a matrix U consisting of orthonormal columns that is dimension n by d, then the 2 to infinity norm of U is bounded below by square root of d over n and bounded above by 1. More generally, let's consider T to be, let's say, n by d. Okay, tall and skinny perhaps, but not necessarily, at least just given what we've written here. So then, well, if this is indeed the maximum of the L2 row norms of T, then this is larger than if we just take the maximum absolute entry of a matrix. Right? So then if we think about just how does this norm relate to other norms, right? T max is less than or equal to T and 2 to infinity. Okay. I mean, we know here this is the L infinity vector norm on matrices, right? We know that is always less than or equal to the L2 norm of a vector. Here's maybe a quick question. We have this representation 2 comma infinity. Can anyone think of is possibly a representation for the max absolute entry norm in the same way? So here, just to be clear, this is simply max over all ij of Tij. 1, 1, okay. So,
Maybe not, no, it's 1 infinity, yeah, sorry. Yeah, so you've got to, yeah, I think it's
so
for 1.
I mean, there are a few ways you can approach it. One might even be a process of elimination. If you know other norms that can be written in this mixed sense. So we know the operator norm is actually the 2, 2 norm, right? So there are two sort of more commonly encountered norms that also appear when you have the same choice in both of these slots. Right? So, I mean, one example is the infinity-infinity norm, which is not the maximum absolute entry, but it's the maximum absolute row sum of a matrix. And the 1, 1 is the maximum absolute column sum of a matrix. So this actually is the 1 infinity norm.
Minor comments should be T there, but
Thank you. Yes, yes. Appreciated. So indeed, we can show this. Okay. And what about, well, other norms that we've talked about are Frobenius and operator norm. Well, indeed, we know that this is true. Now we might ask how, conceptually, how does the treatment of the left and the right-hand side differ in the language of equivalence of norms in finite-dimensional vector spaces? Right? So, I mean, we know that all of these norms. So we have this relationship, but we know that, for example, we can upper bound T in operator norm by T in 2 to infinity norm, but we may pay a price in terms of a constant that depends on the ambient dimension. Right? You know, we have this relationship here, operator norm and Frobenius norm, but we also know that we can take the Frobenius norm, we can upper bound it by the operator norm times a factor depending on the rank of a matrix. Right? So now one question might be, how large can the gap here be between sort of this is our entry-wise, or let's say our entry-wise and row-wise universe, and this is our, let's say, L2 universe. Now, I know I have an L2 appearing here, but this is an overall L2, right? This is a statement about, you know, aggregating over all elements in the matrix. And the punchline is that here, this gap let me rewrite this. So equivalence of norms here depends on factors involving n. N being the number of rows. Right? So when n is much larger, so now let's suppose n is much larger than d, the difference between maximum absolute entry and 2 to infinity is small, right? It's related through d. This gap can potentially be very large depending on the value of n, and these are close to each other as a function of d. Right? If n is much larger than d, well, d is going to constrain what the rank of t is, right? And we know these are related not just through their size, but through the rank, and so then the operator norm, Frobenius norm of a tall, skinny, low-rank matrix are very close to each other. Similarly, if we only have a few columns, then the max within a row and the L2 of a row is not going to be that much different. Right. So the way to make this sort of concept precise would be to check as an exercise what is a lower bound for this in terms of the 2 to infinity norm, which will involve terms perhaps that depend on n and d. Similarly, what is the upper bound for the operator norm in terms of the 2 to infinity norm, and there you'll see a factor of root n appearing. Right. So, I mean, this is highlighting that for certain settings where matrices have these certain sizes, studying these norms separately from these norms can be very useful because the bounds implied over on the left by quantities on the right could be very coarse and could be not even useful. We saw last lecture very briefly that using the infinity norm for the case of a rank 1 vector gave us a benefit in the rate that looked like square root log n over n, right? So almost a factor of 1 over root n that we won by considering this entry-wise analysis. And so the idea here is the same. Okay. So one punchline from this discussion is that if you want very refined bounds in a row-wise or in an entry-wise sense, then you should try to work with both of these norms directly and analyze the matrix perturbations in these norms directly, and wait as long as you can until you have to do something like bounded above by an operator norm or Frobenius norm or something like this. Okay? So direct analysis on the perturbations is needed. Maybe another useful observation is that if we now have A and B in 2 to infinity, this is not, in general, less than A 2 to infinity in 2 to infinity. Let me really emphasize this in red. So this is less than or equal to. Okay, but we do have some convenient properties that we can leverage. So if I have matrices A, B, and C of appropriate dimensions so that I can multiply them, it is in fact the case that we have A in infinity norm, B in 2 to infinity norm, and C in 2 to norm. Right? So if you study norms of this form for general, let's say, alpha and beta, then what you'll learn is that there are these sort of restricted submultiplicativity properties for norms. I mean, we know, for example, that the operator norm is submultiplicative, right? If we have a product of 2. And actually, if we believe that we can switch out these indices with other indices, well, then keeping 2's everywhere would verify that for us right away. So I was a little surprised when I first sort of learned this and discovered this, but to see this, you can construct very simple examples that show it's violated. A useful observation from last time is that for all, let's say, orthogonal matrices, d by d, if we look at A, W, and 2 to infinity, well, applying an orthogonal transformation on the right is acting on all of the rows of this matrix, and we're looking at the L2 norm, so it's unaltered. Right? If we Okay. Okay, I guess I didn't specify dimension here, so this is fine. But if we look at an orthogonal transformation on the left, this is not necessarily A in 2 to infinity. Okay. But if we look at W that are signed permutations, meaning these are matrices of orthonormal columns, each row or column has only a single plus or minus 1. Right? So it's permutations, but I'm allowing a choice of sign flip. Then it is the case that we have this. So let me use a different notation just so we don't get confused. Let's say J. It is the case, well, if we apply a permutation to A, the L2 norm is not sensitive to that. So this is true, okay? So that's nice. What this is saying is that the 2 to infinity norm is somehow not as smooth or sort of unitarily invariant as the operator norm and the Frobenius norm are, right? We know for operator norm and Frobenius norm, we can multiply on the left or the right by an orthogonal transformation. It leaves the norm unchanged. Here, we have one side is okay, but the other side is not, okay? But sign permutations are a special case of orthogonal matrices. So now if we really wanted to, we could go back and say, what about this max absolute entry expression? And the max absolute entry doesn't depend on row or column permutations. So in general, this is not invariant to general orthogonal transformations, but it is invariant to signed permutations acting on the left and the right. So maybe in yellow, for all JK signed permutations, it is the case that, let's say JA in 1 infinity is equal to AK 1 infinity is equal to A. Okay. So why are we talking about these relationships? Well, my hope is that I can convince you, at least in part, that when thinking about point clouds as tall, skinny matrices and thinking about these as configurations in low-dimensional space, it makes sense to not care or to be agnostic with respect to certain reorientations of that point cloud. That's exactly what this relationship here for the 2 to infinity norm is capturing. If we look entry-wise, well, then a transformation could drastically change, or could change the maximum absolute entry of our point cloud just by applying a transformation. Let me pause for a moment and see if there are any questions. Okay, so now going back to this discussion where we have a matrix U of orthonormal columns, we can think of that as a matrix of eigenvectors for some underlying symmetric matrix. This is capturing two extremes, right? A fully delocalized extreme and a fully localized extreme, right? Vectors whose entries are 1 over root n in modulus give us the lower bound, whereas standard basis vectors as our columns would give us this expression. Right. So then this property of an underlying subspace comes up. We saw it briefly last time in the concept of what's called coherence. So often this parameter mu is used. And so here, if our dimensions are, let's see, n by d, then it's convenient to talk about the incoherence parameter as a scaling of, in this case, the squared 2 to infinity norm. Remember that last lecture we saw for the 1D case, this was just n times our single vector in infinity squared. So here. Any questions or comments at this point? Okay. So I want to spend just a moment emphasizing the sort of the underlying details that lead us to bounds of this form on the 2 to infinity norm. I'll leave these up here. We might need to refer to them. I'll erase this proof. Right, so for this example, and the notation that's often used elsewhere is, a star denotes the population quantity, a lack of a star denotes the sample quantity. This you also see. I mean, I've sometimes liked the notation with hats because in statistics we put a hat on a sample quantity or an estimate or an estimator. So in that case, though, you have to be a little bit careful because now the role of the population in the sample have changed. So just be a little bit careful. So we're going to focus, in all these notes, we focus on this notational convention here. For this particular problem, we are looking at top rank R eigenvector estimation, where M star has exactly low rank, and we're interested in exactly the low rank part. There are plenty of existing results that for a low rank setting bound just a subset of the low rank part. And in fact, in some cases, you can do better depending on relative eigengaps. So you could do, even though this is rank R, maybe R is 5, depending on what the eigenvalues look like, you could do better if you just bound the perturbations for the first eigenvector separately and then do dimensions 2 through 5 sort of by themselves. Again, this depends on ultimately like signal to noise ratios for this top eigenspace estimation. But here, M has exactly rank R, and we're looking at exactly the top R eigenvectors of M. Okay, the assumptions here are similar to what we've seen before. Our symmetric random matrix of noise has mean 0. There's a uniform bound on the variance of these elements. We're also assuming that the elements are themselves bounded. This can be relaxed through a truncation argument. What else? So we have a condition number which captures the aspect ratio between the largest and smallest non-zero eigenvalue of m star. And we have the incoherence parameter mu that we defined down here, which reflects the row-wise properties of, well, in this case, really it's u star. U star is our object of interest. And then there's a bit more of a technical assumption which simplifies the presentation. Believe it or not, this is a simplification of a more complicated presentation for the bound, but that boils down to restricting the relationship between these quantities it should not be too. This is big O, big O1. Right. In principle, in this result, R, the dimension, can change with n. The eigenvalue lambda star R is going to change with n. Mu, right? Mu captures both n and in this case R, our dimension. And this just leads to a little bit of simplification and sort of stabilizes what the result looks like. So in the literature, what you'll often find are somewhat general bounds of this flavor, but then after that, more concrete special cases are presented to help us get a better understanding of what's going on. So, this simplifies considerably when we're in the setting that our aspect ratio, or our condition number kappa here, when this is order a constant, let's see, when rank is not allowed to change, so when here the rank that we're estimating is order a constant, and when mu is not too large, so let's say maybe less sim log n. Another way of putting that would be u star 2 to infinity being, well, okay, this could depend on the dimension, and the dimension is taken into account here. So maybe it is simpler just to write it this way. Right. So in this case, the kappas and the r's fall away. We see mu is, well, let me leave this a little bit vague. Mu is small, so we see this factor sigma root r log n. Remember that for our operator norm bounds, we saw what looked like, in the language of this result, sigma times root n over lambda r star. And so we are interested in settings where this bound gives us better control than if we were just to have done the operator norm analysis, right? So if indeed mu is no more than log n, then we've replaced the n in the square root with something that looks like log n, right? Which is effectively a savings of order root log n over n. And this is what we would hope for, given the fact that we have this discrepancy between the number of rows, that's being large, and the number of columns is small. Right. Okay. Questions or comments about this result? So how would we even go about trying to prove these results in the first place, right? It's not so clear. We haven't yet talked explicitly about any of the perturbations themselves. We've talked about the model, all right? We've talked about, okay, compute an eigenvector. In the proof for the L2 consistency, I mean, we used Davis-Gahan and Weil, but we didn't actually have to roll up our sleeves and do any perturbation analysis ourselves, right? We just sort of appeal to those existing results. So now I want to take just a few minutes and highlight some very high-level ideas for how we might start to tackle this, and also why the second line is perhaps interesting. Actually, okay. All right, so M, whoops. All right, just to recall, all of our discussion is about square and symmetric matrices. There are plenty of results in the literature that look at leading singular vectors, right? In the case when your data matrix is rectangular, and these ideas can still apply, but for presentation and exposition, it's just easiest to work with symmetric matrices. Okay, so we have this setting. We have that M star decomposes in this exact low rank way, and I'm going to say here that M looks like U lambda U transpose plus U perp, lambda perp, U perp transpose. This is going to be our top rank R part. This is our remainder. Okay. Now, let's let W be an R by R orthogonal matrix, and let's just think about this expression appearing in the first line. So U minus U star W. Okay, so this difference of matrices of eigenvectors. Anyone have any ideas or suggestions for how we might try to expand this quantity? There's no real hint. Well, okay, I guess there's only one somewhat distant hint, which would be this, but this is several steps removed from what we have here. So this is more of a conceptual or
If I remember correctly, you said that U transpose minus U star transpose was an upper bound?
Oh, okay. So we might think about upper bounds for that, right? You mentioned UU transpose. So that's great because we're talking here about bases for low-dimensional subspaces. We can then partition our space according to orthogonal projections, right? And we can decompose sort of the part that is our principal subspace of interest and then the rest, right? So that's certainly a great idea. Let's do that. Let's do it this way. So we're just going to take this expression here and decompose it according to the orthogonal projection onto the complement of our top K eigenspace and the projection onto that subspace. right? So recall, we just have identity is the same as 1 minus U star transpose plus U star transpose. That's all I'm doing here. Now let's maybe observe that, well, this projection applied to this matrix results in 0, right? Where we keep this factor of U, but then we can also simplify this side because we have this U star transpose U star. That's just the identity in dimension D, or R, excuse me. I apologize. I'm switching between R and D as the dimension, but okay. So then this is U plus, now let's simplify this slightly. This is U star. I'll pull this to the outside, and we have U star transpose U minus W. Okay, any questions or comments about this? Okay. So now, it might be worth thinking geometrically about what some of these expressions are, and what they correspond to. And really what we're doing here is delving into the territory of canonical angles between subspaces. So if you've heard of the CS decomposition, meaning the cosine sine decomposition, this lets us decompose two projections onto the same low-dimensional space and think about the angles between those projection vectors. We talked about last time the equivalence of norms when we encountered orthogonal projections. So U transpose, UU transpose, U star transpose. This quantity, this is related to the canonical angles. This is not equivalence. These are just bullet points. This is related to the geometry between these subspaces. So this is the diagonal matrix, right, of the canonical angles between the subspaces determined by U and U star, and I'm taking the sine of those angles. Let me see. Maybe it's easier to go to one dimension. So if we just have, if I give you vectors x and y of the same size, and I ask about the cosine theta between these. Letter? Okay, inner product over the norm. So maybe I'll write x transpose y over the norm. And I guess we have to be a little bit careful depending on the order, but okay, up to maybe a sign or something like this, that's fine, right? Okay? So we have this. So now if x and y are unit norm, right, then we just have this product, right? In our setting, what we see is a product. This is an R by R matrix, U star transpose U, right? But now, the columns and rows of this matrix are exactly unit norm vectors, and so perhaps there's a higher order, higher dimensional geometry between these collection of vectors in the same way that there is for this, right? And so now for this expression, let's look at its SVD. Let me write this as W1 C W2 transpose. Okay? Here, these are just orthogonal matrices. I claim that we can interpret the diagonal matrix of singular values as the diagonal matrix whose diagonal elements are the cosine theta distances between the corresponding cosine theta of the angle for the corresponding vectors. Right? In the same way that this one-dimensional case, right, up to a sine, well, orthogonal matrices in one dimension are just plus or minus 1, right? There's sort of a sine, perhaps a sine issue here, but this gives us the R by R analog. So this is the diagonal matrix of singular values is, let's use similar notation over here, cosine theta matrix of U star. So over here, I'm just talking about the sine theta U star. Right? And now if we think back to just vectors, or just two vectors, we think about the unit circle, right? Vectors are close or pointing in the same direction when the sine theta is small, right? So perturbation bounds that control this sine theta quantity in, say, operator norm or Frobenius norm tell us that the subspaces are close, right? Davis-Kahan, I'm running out of space a little bit. So Davis-Kahan says that U minus U star W for a specific choice of W, that this is small, provided your signal to noise ratio is appropriate. This implies that UU transpose minus U star transpose here, let's say operator norm. And these are if and only if statements because these norms can all be related to each other. Okay, so saying that this expression operator norm is small is the same as saying the difference of orthogonal projections is small, and that's geometrically saying that the vectors are, in a certain sense, getting closer and closer to each other, pointing in the same direction. Okay, so we have to use some existing, geometric results in the study of matrix perturbations and subspaces to kind of motivate what comes next here. But if you're willing to believe me that these terms are all related and there is this geometric understanding, then we can proceed from here. In fact, okay. Right. So we've rewritten this matrix difference, and now we've noticed that W up until now has been a placeholder. Right? We just started with some general orthogonal transformation, but we didn't specify anything about it. Right? Now we could ask, is there a best or useful choice of W? Right? Okay, and so to answer that question, we can ask, when is, or for which W is this small? Right? If we want to arrive at an upper bound for this, well, presumably we're going to do triangle inequality and some other submultiplicativity arguments. So we, eventually are going to pass all that through to the side, and we want this to be small at the end. I mean, we could, if we want, get to a point where we just then are thinking about, you know, an inf over w of this expression, say, in operator norm. And if we were to spend some more time looking at the analysis, what we would find is that the best choice for this setting is, in fact, the solution to the orthogonal Procrustes problem that we encountered last lecture. So that was the matrix W. That was W tilde. This is arg_inf of u minus u star W in Frobenius norm. All right, so I think Roberto asked last time if the operator norm version of this problem can be solved, and the answer there is no. And even though we're talking about operator norm here, this can be related to a statement here involving the Frobenius norm, and this is the convenient choice. It's also the tractable choice for us. Right. I also mentioned this relationship over here, this submultiplicativity, right, where b times c in 2 to infinity is less than or equal to b in 2 to infinity times c in operator norm, right? So if we think about just this expression here, right, if we think about bounding this in 2 to infinity, right, this is going to be less than or equal to u star 2 to infinity times operator norm of this difference. Now we're suddenly capturing the properties of u star that we're hoping to, right? The bound reflects u star. This is what we want. We incur this operator norm term, and so that's why we studied it just a moment ago. And the claim is that we'll use the orthogonal Procrustes matrix to control this guy. We can be very explicit if we want. In the language of subspaces down here, we can actually show that this in operator norm is less than the squared operator norm of the sine theta between these subspaces. What this is saying is that this is of smaller order compared to actually this in operator norm. This is sort of a residual from our point of view. Right? So analyzing this term gives us a smaller order residual together with the fact that we're keeping information about u star that we began with. Okay. How about another sort of view or line of approach, which is, let's start with U, okay? U is our matrix of eigenvectors for M. Right? Let me rewrite this as M U lambda inverse. Why? Well, I'm taking M, I'm multiplying on the right by U, right? And in this setting, these eigenvectors are orthogonal from these eigenvectors, and so this term cancels. Maybe it's easier if I actually do it in the reverse order. So let's look at M U lambda inverse. This is U lambda U transpose U lambda inverse plus U perp lambda perp transpose inverse U lambda 1. But here, these spaces are orthogonal, so this term is 0. This simplifies to U lambda U transpose U lambda inverse. Now this is the identity matrix. These are diagonal matrices. that are each other's inverse, so this whole term cancels, and we arrive at just u. Right? So we have u is equal to m u lambda inverse. Okay? Now, m, our observation, is modeled in this signal plus noise way. Right? So we have m star plus e u lambda inverse, right? Just plugging in. Okay? Now let's expand. Okay? Now let's again think about projecting onto the subspace spanned by the leading eigenvectors that we're interested in, right? And their complement separately. So we have m star here, u star transpose. Plus, let me write this as E I minus u star transpose u lambda 1. Okay. So now, the claim excuse me. Excuse me. Let me change this slightly. Yes. So all I'm doing is I'm saying, okay, we know u is equal to mu lambda inverse. And now I'm going to take this idea, but in a slightly more complicated way. I'm going to write this orthogonal projection as u star inverse lambda star, right? So these cancel. U star transpose u lambda inverse plus m times the orthogonal projection u lambda inverse. Okay, so now we have to make a few claims. So this is approximately, so in the perturbation analysis we can show this is approximately our W tilde, the orthogonal Procrustes problem. There's going to be an approximate commute argument in the sense that we're going to be able to move this to the right-hand side, and we're going to get approximate cancellation between these expressions, and that leaves us just with m u star lambda star inverse. W tilde. Okay. Now for this term, we have m, right, which is m star plus e, right? But this is a projection onto the orthogonal complement of m star. So m star vanishes, and we're just left with e. Okay, and so it's these high-level ideas that lead to this second line here, which is not comparing the sample eigenvectors to the ground truth, but to a transformation, if you will, that still involves the data multiplied on the right by these population terms. Okay, a very sort of high level and quick sketch. Questions?
One reason to have equation 21 besides equation 20 is that somehow you get this lambda r squared in the denominator, and that cancels more things in the numerator. Is that the way it works?
That's right. In some cases, that's right. In some cases, you can show that you are actually, your sample eigenvectors are closer to this expression than to the underlying population eigenvectors. That's right.
Does that make a difference in the actual rates you get?
It can, yes. So in some cases, what that means is you need an additional refinement step to actually achieve an optimal rate. That's right. That's right. Okay. So let me give you sort of an answer to a lot of the perturbation analysis here. So I claim, let's see. I claim that U minus U star W, right, so for this special choice of orthogonal matrix, that this is equal to the following. Okay. Okay. So in some sense, this is a trivial statement because I'm saying this is equal to this plus something where I haven't specified this, right? So this could just be the difference, and we call it a day. But the idea is that the row-wise properties of this matrix are reflected in this, and this is indeed a smaller order term. To infinity, let's say plus like little op1 or something. Right. Now, this quantity, or really quantities like this, appear in the derivation of the Davis-Gahan theorem. Right? So for Davis-Gahan, the first version I think mentioned in the lecture notes actually said that if we look at the operator norm distance, this is less sim EU operator norm lambda r star. And in fact, really for Davis-Gahan, what we encounter is I minus U star transpose E U, and we can even say U star transpose in operator norm. Right? But in many settings, this is just essentially E in operator norm. Right? Instead, by going directly to the perturbation analysis and isolating this term and sort of other terms like it, that allows us to get more refined results. Right? And in particular, what we have in this setting is even sort of a stronger statement, which is that often this projection, or the projection, yes, this projection is small when U star is delocalized. So in fact, we have a stronger statement which is that this looks like E U star lambda star inverse. Okay. Why is this significant? Well, this tells us that in a certain sense, in certain settings that can be made precise, the effect of this perturbation on the top eigenspace is approximately linear in the error in E. Right? So let me rephrase this slightly just to make that point a little clearer. So we have that U is approximately U star W tilde. Okay, I apologize. I need a W tilde here. Yes. Plus E U star lambda star inverse W tilde. A moment ago I talked about the difference of these two. What I'm saying now is that the perturbation, the sample eigenvectors are a perturbation of the population eigenvectors, and the leading order term looks like this, which is linear in the error E.
So would that be good enough to prove some sort of asymptotic normality?
Yes, exactly. This is exactly what we use for asymptotic normality, because we look at the rows of this matrix. Exactly right. Yep. There's another, okay, yeah, okay. I promised you a discussion of some other proof techniques, so let me live up to that promise. Okay, this will correspond to the final 2 pages on this PDF, which are either fortunately or unfortunately blank to be filled in here. I can actually jump ahead to this. So this higher order concentration, well, it's there, so I don't need to repeat it. Okay, we have, in our discussion of E and operator norm from last time, that this looks like, with high probability, let's use our notation for the random graphs, n rho to the 1/2, right, from last time. Now, what we're saying is for this row-wise and entry-wise analysis, we have something like this, and we're really interested in picking out rows of this, so multiplying, right, standard basis vectors picks out rows of this and rows of this residual here, right? So really what we care about is E, looking here, E left multiplied by a standard basis vector and right multiplied by some delocalized vector V, right? Picking out a row of E and then looking at the linear combination that row of E induces with the, say, first column of U star, right? Okay, and so we want to control this, and in fact, we're going to want to control this for E raised to powers T, okay? Now we can do this. This was developed in at least back to 2013 by Laszlo Erdős and colleagues in the context of random graphs getting results for sparser and sparser concentration, involving combinatorial techniques, right, to handle these powers of T. This was then applied in the context of mixed membership stochastic block model graphs in this JAZA paper by Purna Sarkar and her group, and has appeared elsewhere as well, but these are sort of the 2 key places for the purposes of this mini course. What we have here is that there are indeed bounds on this quantity, but they look like this. Okay, so this is for t. Well, really it's, so the good news is we don't have to do this for all possible t, but we only have to do this for logarithmically many, but it gets harder the further you go out. So what are we doing here? Well, we're capturing this, 1/2 correspondence to the first power for higher powers of t, right? E to the t, and we have t over 2 times n rho, okay? Now, what we win is a factor that depends on the extent to which v, this fixed non-random vector of interest, is delocalized. This is the L infinity norm of v, right? So in many cases, this looks like order 1 over root n, right? Possibly up to additional logarithmic terms. And we have this additional log term depending on t, and possibly multiplied by another absolute constant, little c, right? But what this is saying is that ultimately up to some log terms, we're winning by a factor of, say, 1 over root n by considering this product directly, right? So if we naively bound this in operator norm, right, we would only get this expression here. Right. And so now, how do we apply this? Well, we can do this, if the probability statement is strong enough, which it is, we can do something uniformly over all rows, meaning over all n standard basis vectors, right? And we can do this for all columns of U star when we're in the multidimensional case. Okay? Right. So if you'll bear with me for just another moment, I will deliver on my final promise for sketching leave one out. Consider a rank 1 spiked model. We're going to define some auxiliary matrices in the following way. We're going to let m to the L denote the same rank 1 spike, but plus a modified noise matrix, E sub L, where E sub L, its ij entry, looks like the ij entry of the original noise matrix if I is not equal to L and j is not equal to L, and it's 0 otherwise, right? So pictorially, E looks like this, and EL takes this matrix and zeroes out the Lth row and Lth column. Right? So by doing this now, the randomness in the row and columns are independent, right, for these different choices of L. Okay. So here's a sketch for the pipeline. We have U is our top leading eigenvector for M, our sample, right? This is what we compute. The claim is that because we are holding out only a relatively small amount of the noise, this eigenvector is approximately the same, or is very similar to the top eigenvector for the ML up to a choice of orientation for each L. This is true, right? So we have In this symmetric case, right, we have order n squared random variables, but we're only leaving out order n here, and so perhaps it's believable that that difference is small, okay? So we have this. Now, let's look at this expression, and in particular, let's look at the lth element of the leading eigenvector for ML, okay? Well, by definition of what it means to be an eigenvector-eigenvalue pair, let's write this in this way, right? We just have the matrix, right, multiplied by the eigenvector, and then divide out by the eigenvalue, right? Okay. Now, by construction, notice that the lth row and column of ML is the same as M. Star, excuse me, the same as M star, right? So this looks like M star, lth column, Uvec L. Okay? Now, let's rewrite this as lambda star divided by lambda L, and this is now U L star U star transpose, this vector multiplying UL. Right? So this is just by definition of eigenvalue-eigenvector pair. This is just by the relationship between the construction of ML and our original M star. And now this is just writing this column vector, the lth column vector, as a scaled product here. Now the claim is that this is approximately this quantity. Because the claim is that this, this product of unit norm vectors is approximately 1, and this ratio is stable. Right, so a very high level. You get cancellation here. So what we've shown now is that this sample eigenvector, right, is close to this proxy eigenvector, right? Now fix an L of interest, say the first one. The first element of this lth approximation is very close to the first element of the original vector, right? So we've constructed this sort of this interpolant, if you will, and we've said that the sample is close to the target through being close to this sort of intermediary role. And we can establish this in a uniform sense. Note, this is a statement about all entries, right? So each entry of our sample has this corresponding approximation, and we can do so in a way that's sort of uniformly strong. Okay. All right. Thank you so much for your patience. I apologize for going over time. It's been a pleasure to be here with you all.